Welcome to 569 Emergent States of Matter for Monday, April the 12th. And we're going to carry on right where we left off, deriving the Ginzburg-Landau equations, which you can see here on the left. So what we derived last time was we said, let's suppose that there is a superconducting order parameter which describes the wave function of a condensate made up of composite bosons which originally derive from electrons. And so we asked what the free energy would look like, at least near the transition. And what we saw was that we could expand the superconducting free energy density as a power series in the absolute value of psi squared. Of course, psi being a complex number, we need to make a scalar out of it. And so the scalars that we can make are out of the quantity psi squared. So what we saw last time was that above and below the transition, the form of this free energy had the forms sketched over here, namely either 0 above Tc or below Tc, there was a degenerate minima. And the degenerate minima is defined by the fact that the absolute value of psi is given by a constant, as shown over here. But the phase of it is left arbitrary, and so that means that you have a degenerate set of solutions. So what we want to do now is include the effect of spatial variations. So we're going to include and the usual way that we would do this is we would write down grad psi squared as the kinetic energy term, or not really kinetic energy, but the gradient term in the free energy functional. However, we're going to have to make a change in this case, because we have here a charged condensate. And what we would expect is that in general, if we have a wave function, then the gradient term is really something like h bar squared over 2m grad psi squared. Del squared psi, like so. That's what we would expect. And this is just basically p squared over 2m times the wave function psi, where p is the operator minus a h bar grad. So that's what we would expect in regular quantum mechanics, where psi is the wave function for the Cooper pair. But because it's charged, we know that the canonical momentum for a charged system is not p, but p with a term that reflects the vector potential. So the canonical momentum for a charged system is the following. It's basically p minus e over c times the vector potential. So the momentum operator goes to this form as I've written down over here. So that's the first change. The second thing that we need to remember is that that psi represents a Cooper pair, and as such has charge 2e. So what we might guess then is that our momentum operator is going to go to p minus the effective charge, which is 2e over c times a, and that would be because we have a Cooper pair. So this factor of 2 would be an exact result. So what that means is then when I now replace P by I H bar grad and write down what the form of the kinetic energy is, what that's going to mean is that where I would normally have expected to have the operator grad psi, taking into account the factors of I and H bar and so on, well, that's going to go to, in fact, grad psi minus 2I E A over H bar C. And so the gradient term is not going to be what we would normally have expected for a neutral superfluid, for example, but is going to have this gauge dependent term here. And in the homework, you will verify that that this allows the system to obey a gauge invariance. So in homework, you will verify that this is necessary, so it satisfies gauge invariance. So I'm not going to delve into that right now. I'm going to then summarize how I want to put the free energy together. So let's now put the free energy together. In units that sort of reflect this heuristic derivation. So we're going to have a free energy functional, which is now going to depend upon the psi field for the superconducting order parameter and the vector potential, and that's going to be equal to the free energy in the normal state, and then a term that depends on the vector potential. Now the vector potential satisfies B as curl A, and we're going to assume that B and H are the same because mu is equal to 1 for most metals. So we're going to write the kinetic, the potential energy of the external field as curl A squared over 8 pi. So that's the field term, and then the uniform part of the free energy, which we wrote down last time, is something like that. And then lastly, the gradients terms, which have the form that we've just motivated. So I'm going to just write this coefficient out in front as h bar squared over 4m, and then grad minus 2I E over h bar C A, acting on psi squared, and then that is the full free energy, and then we integrate this over space. And so this is a free energy that depends on both the gauge field and the order parameter. And I want to just add these annotations to this. So here we have a factor of 4m, because we're saying that the mass is equal to twice the mass of an electron. And here we're saying it's a factor of 2, because the charge, let's call it E star, is effective charge. Is equal to 2E. Now, I do want to make a comment about this term over here, this term. In fact, you will later see that nothing depends on what we choose for the mass. So this coefficient here is physically meaningless. But this coefficient here has meaning. Because it tells you how the gauge field couples to the order parameter. And so it's physically meaningless because it is a normalization, basically. And so effectively you scale it away. So we're not going to really care too much of it. But this is the people, if you look in textbooks on superconductivity and articles, people, particularly experimentalists, often like to write it in this way. You know, it's not really, again, all the caveats that I just said, don't worry too much about the heuristic nature of this, because it's basically all determined by symmetry. You have to have a gradient of the order parameter. The order parameter is charged, and so what we need is that the gauge invariance here. I'm just going to make this comment. The gauge invariance that we're talking about here is that I can make psi go to psi times some phase factor, and simultaneously I can absorb that phase factor into A by making A go to something like minus grad phi, something like that. So basically, so basically the point of our gauge invariance is that a change in phase of the superconducting wave function that gets absorbed by a change of gauge. Of the electromagnetic vector potential, and that has profound consequences. And so this is what we mean when we say making a gauge transformation. Okay, so now that we've got that out of the way, let's go on to write down the so-called Ginzburg-Landau equations. So the fundamental physics of this is that the Ginzburg-Landau free energy should be minimized in equilibrium and so we need to minimize with respect to psi, and A. Now, psi, of course, has got a real and imaginary part. So we can either choose the real and imaginary parts, although it's equivalent to just choose psi and psi star, its complex conjugate, and think of them as being independent variables. So this has two components, the real and imaginary parts. This is one quantity, but it's a vector, and we'll get into the vector part of it later. And so there are basically three independent functions that f needs to be varied with respect to. So what people like to do is we could choose these to be the real part of psi or the imaginary part of psi, or equivalently, we can say it's psi and psi star, pretending that psi and psi star are different variables. If you know psi and you know psi star, then you can construct the real part of psi and the imaginary part of psi. So these are really equivalent things to do. So psi star regarded as independent. And the thing is that it's nice to do that is because it's so easy to write down what the equations are, whereas in the real and imaginary representation, it becomes more complicated. So let's go ahead and take the variation with respect to psi. So what we're going to do is essentially just a functional derivative like you did in first homework, but I'm going to do it just slightly more slowly. So I'm going to write variations with respect to psi star as the first thing that we do. So what we're going to say is that if I take a change in psi, then I'm going to ask what kind of change does that make to the free energy. So let's write that down. So delta F is then going to be the following, and you can check this yourself. So it's going to be this. So there's going to be two terms, minus h bar squared over 4n grad minus 2ie over h bar c a squared psi plus alpha psi plus beta psi squared times delta psi star, and that's all integrated over R. So all I've done is I've replaced psi star by psi star plus delta psi, put that into the form and computed what the change in the free energy is. Okay, so all I've done is I've made F go to F plus delta F, psi star goes to psi star plus delta psi, etc. And that's how I got the equation up here. Okay, now this is all true, but there's also a surface term, and we're going to have to worry about that surface term. So let me put a big plus in here just to make sure that you realize the equation is continuing. And then the surface term that you get, and I'm going to write it down, and you can check this, is h bar squared over 4m, the surface integral over the domain that we're talking about, of grad psi minus 2 ie a over h bar c delta psi star times n ds. So this thing over here is on the left of the n is a vector, of course. And ds is a unit of area. N is a unit vector perpendicular to the surface. And you know, this boundary term is usually neglected in variational calculus, but we're going to include it here. So this boundary term comes essentially from doing integration by parts. So this boundary term is usually neglected. In the calculus of variations. But we're going to need it, and you're going to see why we need it right now, because our condition for equilibrium is that delta F is equal to 0. Okay, all these functional derivatives have to be 0, and so the only way that we can achieve that is that if what is in both of those integrals on the previous page are equal to 0, and so in order for the boundary term to vanish, we need the following condition, that n minus I h bar grad psi minus 2 e over c a psi is equal to 0, and this term, this condition is basically saying that that this is the normal vector. This is like a current is equal to 0, and so what it's telling us is that there's no current flowing out through the system. So we're imagining, and here is our volume of superconductor. Here is our element of surface area, like so, of magnitude ds and direction n. And then what we're saying is that there is no, that this condition means that there is no current out of the system. Okay, so that's the condition for the boundary term. And then if we look at the volume term, then what we get is everything inside the curly brackets we want equal to be 0, because we want delta F to be 0 for arbitrary variations of the order parameter. And so that means that we get the equation 1 over 4m minus I h bar grad minus 2 e over c a squared psi plus alpha psi plus beta psi squared is equal to 0. And this equation is a famous equation and is known as the Ginzburg-Landau equation. So what it says is that if I have if I want to know what the order parameter obeys in a superconductor, it has to be the solution of this differential equation here, where A is the vector potential for the external applied field. Okay, so that's variation with respect to psi star. So how about variation with respect to psi? And of course, that's just going to be the same thing as the complex conjugate of the above equation, so nothing special. So there's no real new information. So then the next thing we have to do is we have to do a variation with respect to the gauge field. Variation with respect to the gauge field. And so again, I'm going to not expose all the algebra. I'm just going to simply write this down, and you can check this. So delta F is equal to the integral d3r. Okay, and now remember, I'm going to write h is equal to curl A. I'm going to define this field H. That's the external field. I'm writing it down as a little h. I don't really know why, but that's what I wrote in my notes. So if I now differentiate with respect to A, I'm going to get the following terms: curl H over 4 pi minus E over MC psi star minus I h bar grad minus 2 E over C A times psi plus the conjugate of that. So it looks like this: I h bar grad minus 2 E A over C psi star. And then that's multiplied by the variation delta A. And so that's what you get. All I've done is literally wrote A goes to A plus delta A. So, and seeing how f goes to f plus delta f, and then subtracted them, and this is what you get. So go ahead and try that. And so what we need to do is we want to set df by dA to be equal to 0. That's the inside of the brackets. And the thing that we're going to see is that, of course, we have from Maxwell's equations that the curl H is equal to 4 pi over C times the current J. And so what this then gives you is that we get that curl H is indeed equal to 4 pi over C J, where J is equal to E H bar over 2 I M psi star grad psi minus psi grad psi star minus 2 E squared over MC psi squared times the vector potential A. So this is the current, and this current is in general equal to the normal current plus the supercurrent, but the normal current is going to equal 0 in equilibrium, because you've waited a long time and it's gone to equilibrium, it's dissipated, and so the only current you're going to get left is the supercurrent to JS. So we've got an interesting result here, which is telling us that this current, which is indeed the thing that we wrote up over here, this current is indeed equal to 0 on the boundaries of the superconductor. So this confirms our boundary condition interpretation and J dot N is equal to 0 is equivalent to no current enters or leaves in equilibrium. Okay. All right. So that's what I'm going to. That's where I'm going to leave the boundary conditions. Let me also make a comment about the boundary conditions for the external magnetic field. So we know that that J, the current, is finite, and is also tangential to the superconductor, because we know we know that there is no current out of the material. So so what that means, because J is tangential, that means that curl H is tangential component is also finite at the surface of the superconductor, and so the tangential component is therefore continuous. At the boundary of the superconductor. Now, the other thing that we know is that, of course, that H satisfies div H is equal to 0. And so that means that H dotted with N is continuous also at the boundary. And so, so what we've learned then is that both the normal and tangential components are continuous, and so therefore the field H is continuous at the boundary. So if you think of a superconductor as having sharp boundaries, which we can't really do, we shouldn't really do that, as you'll see. Then we expect that the external magnetic field in this formalism will vary in a continuous way. Now, so that may seem, so if this seems a little bit arcane to you, that's fine. Don't worry so much about that. But you'll see where we're going with this in the next section. Okay, so now what I want to do is I want to talk about the characteristic length scales that govern the behavior of superconductors in this Ginzburg-Landau description. So this section here is on the characteristic length scales. So what we're going to point out, so our goal in this section is to show that there exist two independent length scales that control the behavior of superconductors, and the first of these determines the correlations and behavior of the order parameter itself. So they in fact will give you the correlation length. The second one is going to govern the behavior of the vector potential. And so that's going to give you what's known as the electromagnetic penetration depth. Okay, so let's look first at the electromagnetic penetration depth. So what I'm going to assume is that we're going to set alpha less than 0, which means that t is less than tc. And we know then that psi squared has a magnitude alpha over beta. So that means that if I then go and put that into my description for the current, then the gradient terms vanish. And so what I get then is that J is equal to minus 2 E squared over MC psi squared A. And if we think of psi as being normalized by 1/2 the number of superconducting electrons, then we're going to think of that as minus n E squared over MC times the vector potential A. And this equation is known as the London equation. And we can we can use this equation to determine how a magnetic field varies in a superconductor, or really, I should say more precisely, close to a superconducting boundary. So the picture that we're going to have for now is the following. I'm going to assume that I have a superconductor over here. This is a superconductor. This is normal. I have space going in this direction here, and what we want to understand is if I have an external magnetic field H, how does it vary as a function of x as I go into the superconductor? So the way that we solve that problem is by writing down again Maxwell's equations. So we know that that curl H is given by J over here, and J is given in terms of the vector potential, like so. So so the strategy is to take the equation to take Maxwell's equation and take the curl. So what do we get? So on the left-hand side, we're going to get curl of curl H. And curl of curl H is grad of div H minus del squared H. That's a vector identity, but div H is equal to 0 from Maxwell's equation. And so this thing is just equal to minus del squared H. Okay, so that's the left-hand side. Now the right-hand side of the equation is the curl of 4 pi over c times j, and because j is equal to minus 2e squared psi squared a, when I take the curl of it, I'm going to get a factor of curl of a, and curl of a is equal to h. And so this is equal to 4 pi over c times 2e squared over mc, the magnitude of the order parameter psi squared, which is alpha over beta, and then curl of a, and curl of a is just equal to h. And so this is 4 pi over c, 2e squared over mc, oops, alpha over beta times h. So what we've got then is this equation, del squared h is equal to 4 pi over c, 2e squared over mc, alpha over beta times h. And let's look at the dimensions of this. So over here, this has dimensions of 1 over some length squared times h. And so this thing is h over here. And so this thing here must also be a 1 over some length squared. So what length is that? Well, it's a length that we'll write it as 1 over lambda squared h. So we're going to define this thing to be the London penetration depth after Mr. London. And we can read off what it is with this identification. We can see that the lambda L is equal to m c squared beta over 8 pi e squared alpha to the power 1/2. And so we saw that alpha went like T minus TC. And so that means that this thing goes as some lambda L 0 times T minus TC over TC to the power minus 1/2. So what it tells you then is that the magnetic field decays into a superconductor with a length scale that diverges as we go towards the critical temperature from below. So I'm going to just write that down. So to summarize, del squared H is 1 over lambda L squared H has solutions that go like e to the plus or minus x over lambda at the boundary. So going back to our picture on the previous page, here is x, here is h, and let's draw at h equals 0. Let's suppose that here we have a superconductor, here we have a normal. So then what we've just deduced is that the correct solution for this differential equation is going to be, as we go to plus x, obviously the solution that goes as e to the minus x over lambda. And so if we start up with some h naught outside the superconductor, then it's going to decay to 0 inside the superconductor over a length scale of order the London penetration depth. And that's why it's called a London penetration depth, because it predicts that on the surface of a superconductor, magnetic field dies rapidly over length scale lambda to 0 inside the superconductor. And so the fact that it goes to 0 inside the superconductor is what we've seen as the Meissner effect. H equals 0 inside the superconductor, which is the Meissner effect. So the interesting part about this is that the length scale governing the decay of magnetic field as we go into a superconductor is temperature dependent. And as we go to TC from below, this length scale diverges. So you might wonder what this thing physically means, because it's kind of a little strange, because it says that the range of a magnetic field inside a superconductor is finite. Now, usually, if you think about what little you might know about quantum electrodynamics, you would say, well, the reason that we have propagating magnetic fields, electromagnetic fields, is because the photon is massless. And so the massless particles in quantum mechanics have infinite range. And so the fact that we have now an electromagnetic field that has a finite range, it's almost as if the photon inside a superconductor has acquired a mass. And that actually is part of what is known as the Anderson-Higgs mechanism. And in the homework, you'll get to work that out for yourself and see that analogy. So I'm just going to mention this, but I'm not going to really go into it in great detail. So the interpretation is that for t greater than tc, H is infinitely ranged. And so the photon is massless. But for t less than tc, H has a finite range. So photon is essentially massive. And you'll get to work that out in not the current homework, but the one after that. Okay, so that's the length scale that governs how magnetic fields vary inside a superconductor. And now I want to talk about the length scales that govern how the order parameter varies. So the next thing we're going to talk about is not the electromagnetic penetration depth, but is the Ginzburg-Landau correlation length. Okay, so we're going to set the electromagnetic field equal to 0. We're just going to basically ignore this, and we're going to study the spatial variations of psi itself. So let's just set A equal to 0, and then the Ginzburg-Landau equation that we have is like this: minus h bar squared over 4m del squared psi. There's really no vector sign under here. Plus alpha psi plus beta psi squared, and that's equal to 0. So if we had a uniform state, homogeneous, spatially uniform, and the spatial gradients are equal to 0, and we just get the psi squared is equal to minus alpha over beta. And we'll just define this value to be psi naught squared, some real value like that. Okay, so the question I want to understand now is, if I have a boundary between, say, something normal and something superconducting, how does the order parameter vary at that interface? So the question we're going to understand now is, at the boundary of a superconductor, how does psi vary? So basically what that means is that we expect the following picture. So here's our picture for the superconductor. So here we have a superconductor, here we have something that's not a superconductor. So that's the superconductor in here. And then what do we expect the order parameter to be doing? Well, we know that the order parameter, if I want to plot psi up here, we know that psi is going to be 0 outside the superconductor. And then inside the superconductor, it's going to have the value psi naught, like that. And what do we expect to happen? Well, we kind of know the answer, because it's sort of obvious that you've got a differential equation. So what's going to happen is that the order parameter is going to gradually go up from 0 and eventually equal the value in the bulk. And what we want to understand is how quickly it does that. And so we want to understand, what is this length scale? So let's go and solve the equation now, pretty much the same way that we did for the Gross-Pitievsky equation describing a quantum vortex. So the way we will do this is we'll define a variable which I'll call f, which is psi of r normalized by its value in the bulk, psi 0, and then we can see that minus h bar squared over 4m psi naught del squared f plus alpha psi naught f plus beta psi naught cubed f cubed is equal to 0. And so I can write this as a minus h bar squared over 4m psi naught over beta psi naught cubed del squared f plus alpha psi naught over beta psi naught cubed f plus f cubed is equal to 0. And then, of course, I know that psi naught squared is equal to minus alpha over beta. And so this I can write as h bar squared over 4m times alpha times del squared f minus f plus f cubed is equal to 0. And of course, because this is a del squared, then we can see that this term here must have dimensions of length squared. And so we're going to define that length as follows. We're going to call that length scale psi. So I'm going to define psi squared to be h bar squared over 4m alpha naught t minus tc over tc, like so. And so my equation then is psi squared del squared f plus f minus f cubed is equal to 0. And so in one dimension, the solution to this is a hyperbolic tangent. So let's solve this in the one-dimensional geometry that we have on the previous page. So so we can solve it exactly. But for now, just look at the asymptotes. So I'm going to write that f is equal to 1 plus g of x, where g of x is much smaller than 1. So basically what I'm trying to do is in this region over here, we're trying to understand what it is that governs this length scale over here. And so if you substitute that into the differential equation and linearize, what you find is that g double prime is equal to 2 over psi squared times g. And of course, the solution to that is again an exponential function. And so therefore, once I know what g is, I can write down what f is. And so I simply get that f is equal to 1 minus e to the minus the square root of 2 times x over psi of t as x goes to plus infinity. And so what we've just learned then is that the order parameter in the superconductor relaxes to its bulk value over a length scale psi, where psi is given by this formula over here. So this thing is called the Ginzburg-Landau correlation length. And you can see that this correlation length diverges as we go towards the critical point. as T tends to TC. And so I've basically talked about this as if we're starting from below the superconducting transition. Above the superconducting transition, it describes the behavior of fluctuations, but I'm not going to go in and talk about those right now. Well, am I or am I not? I need to make a decision. No, I'd prefer not to right now. I'm going to instead go and talk about type 2 superconductivity. Okay, so let's move on then to section 4.11. And I want to talk about type 2 superconductors. So I want to explain to you now why it is that as you change the parameters that control superconductivity, you can go from a state that is a type 1 to something that behaves like type 2, and so that's going to be the goal of this section. So the goal of this section is to explore the interplay between psi and lambda, and see how this gives rise to type 2 superconductivity. So let's now think about what we've just learned. We've learned that there's two superconducting length scales. There's the penetration depth and there's the Ginzburg-Landau correlation length. So I can make a dimensionless parameter that tells me about the ratio of those lengths, and that dimensionless parameter is called kappa, and we are going to define it in the following way. So we're going to define kappa to be the electromagnetic penetration depth, lambda, I'm going to drop the L, divided by psi of t. And you'll see that both psi and lambda vary in the same way in Ginzburg-Landau theory. They both diverge, and they both go as the square root of t minus tc near the critical point. So this in this theory, this is a constant in Ginzburg-Landau theory, and we're going to look at what happens as we vary kappa. Now, how can we vary kappa? Well, kappa only depends on material properties. And those material properties are the alpha and beta that are in the Ginzburg-Landau free energy. So it'll depend on the quantity psi naught. It'll depend on the quantity that we called lambda of naught in the variation of the electromagnetic penetration depth. So in principle, I can make different materials, and they will have different values of kappa, and you'll just have to figure out by experiment what those values actually are. Okay, so to answer this question, we're going to examine the surface of a superconductor again. And we're going to look at the energy and look at the energetics near that surface. So let's do that. So let's look at the surface energy. I'm going to first look at the situation where the correlation length is much larger than the electromagnetic penetration depth. So kappa then would be much less than 1. So let's draw a picture then of what we expect to see. Again, basically the same kind of picture that we've seen already. I've drawn this now several times in this lecture. So here's space, and then on the vertical axis, I'm going to be plotting two different things. We're going to be plotting the electromagnetic field, or the H field, and we're also going to be plotting the order parameter. So let's do that. Let's start off with the external magnetic field. So the external magnetic field is going to come in like this, and so this is the let's just label this. This is going to be the normal phase. And then over here is the superconducting phase. All right, so the external magnetic field is coming in like so, and then it's going to decay to 0. It's meant to be 0. And it's going to do that over a length scale that's of order lambda. Okay, something like this. Now, what is going to be the value of HC, of the external field? Well, if we're looking at the boundary between a normal and a superconducting region, then the two phases are in coexistence. And so that defines the critical field HC. So this value over here is just equal to HC. So this is the behavior of the external magnetic field as a function of space. Now, if we then draw what the superconducting order parameter is going to be doing, so we know that inside the normal state, that's going to be equal to 0. So that's something 0 out here. And then in the bulk of the superconductor, over here, it has some value which is going to be psi naught. And so what we know is going to happen is going to sort of go up like this. And some hyperbolic tangent, and asymptotically approach its value in the bulk like that, and that length scale is going to be given by psi, and I'm going to sort of sketch it like that. And so that's the picture that we have inside the superconductor. Okay, so the question I want to ask is, what is the energy associated with this boundary between the normal and superconducting regions? Well, of course, in general, we'd have to compute it by solving the Ginzburg-Landau equations, and we have to be very careful about that. But we can more or less see physically what's going on by a physical argument, and that's what I prefer to show you. So this is the question, and so the answer is we could solve the Ginzburg-Landau equations, but it's easier to understand the physics. As follows. So how do we understand it? Well, the trick is to imagine that the boundary was infinitely sharp. So we know the boundary isn't infinitely sharp, but let's ask what would happen if it were. So if the boundary were not smooth, it was infinitely sharp, then the energy would just be the sum of the normal and the superconducting states. So with the sum, the energy would be the sum of the energy of the normal part plus the energy of the fully superconducting part. So it would look something like, oh, great. What have happened here? Okay, sorry about that. So it would look like the energy of the two parts. So let's draw what that would look like. So here is my x-axis, like so. Here is the boundary. This part on the left is the normal part. This part on the right is the superconducting part. And what I mean by saying that the boundary was infinitely sharp is what I mean is that over here, psi is exactly equal to 0. And over here, psi is exactly equal to psi naught. And if I have a system which has a length Ln, which describes the length of the size of the normal part, and a length Ls for the superconducting part, then it would be in this part over here, it's just the normal part. In this part over here, it's just the superconducting part, and I add the energies together in the way that you would have. So that's what happened if the boundary was sharp, but it's not sharp. And so actually the boundary is not sharp. So what difference does that make? So it's not sharp, but because we're looking in the limit that psi is much larger than lambda over here, then the actual variation, the way it differs from this sharp picture, is mostly because of the order parameter rather than for the magnetic field. So actually the boundary is not sharp, and so what we actually have is something like this. So here's X. Here's our boundary between the normal and superconducting states, like so. On the left-hand side, psi is equal to 0, and this region has length Ln, like so. But on the right-hand side, we know that what's really happening is that the superconducting order parameter is going up from 0 and reaching its asymptotic value only over a region of order psi. So it's really basically going like this. And so if I look at this picture, then what I can see is that in this region over here to the right, a region of size, the length of the superconductor minus the correlation length. In this region over here, you have the full superconducting order parameter and the full energy of the superconducting state. And then in this region here, the region of order psi, you actually don't have full superconductivity. So we can say that in this region over here, we don't have fully superconducting in that region over here, and that has the implication that this is then going to raise the energy of the system. So the energy is greater than what it would be for a sharp boundary. Now, why do we know it's greater than? Well, remember that the reason you go into a superconducting state in the first place is because you gain energy by being in that superconducting state. And so the reason why I say greater is because you have not lost as much condensation energy as you otherwise would. The superconductor forms because it has lower energy. Due to the Bose condensation, due to the condensation of Cooper pairs. And now you don't have as much region of superconductor. And so therefore you haven't got as much loss in energy. You haven't reduced the energy by the full amount. And so that's why this system has got a higher energy than it would be if the interface was really sharp. So I can say that the fact that superconductivity only arises after a distance xi into the sample means that you have not lost as much condensation energy as we would have if the interface were sharp. So what does that mean? Well, if the interface was sharp, we know what the free energy difference would be. So for sharp interfaces, what we know is that the normal regions has a free energy density greater than that of the superconducting by an amount hc squared over 8 pi. And that's the result that we found early on. And so what that means then is that our smooth interface, our non-sharp interface, has energy, which I'm going to call E boundary or E wall, the wall between the normal and superconducting state. So that's basically going to be something like this. It's going to be the volume that we have over here, this volume, which is not fully superconducting, that now is more or less normal. So that's going to be roughly, how long is that region? Well, it's of order psi. Then we have hc squared over 8 pi times the cross-sectional area. And so that is the energy cost of having this non-smooth boundary. So in other words, the energy is raised by an amount of order psi times hc squared over 8 pi. So that's the implication of having our system have a non-smooth boundary in the limit where the correlation length is much larger than the penetration depth. So now let's look at the situation, which is the other way around. So now let's look at the situation where the surface energy when lambda is much larger than psi. So we're going to look at the opposite limit. And I'm sure you can guess exactly what's going to happen, but let's draw the picture in any case. So here we have our boundary. Between the normal and superconducting regions. So here we are like this. Now the H field is coming in like so. And is going to 0 over a distance which is of order lambda. So let me draw it like so. And then let's have a look now at what the superconducting order parameter is doing. Well, that's equal to 0 over here. And then very quickly comes up to its asymptotic value of psi 0 over here like so. So that's the picture that we have in this case. So now what we have is that in this situation, now it's the other way around. We have that psi is apart from a very small region. Psi is equal to psi naught throughout the superconducting region. That's not true for the magnetic field. And it's not true for the magnetic field in a region of extent roughly lambda. So in this region, what's happened we have lowered the energy of the superconducting state by the condensation energy of the Cooper pairs. But we didn't have to pay the price of expelling the magnetic field. And so that means that if I want to work out, then what is the energy of this wall, this boundary, this domain wall, if you will, between normal and superconducting regions, then this energy is going to be negative. Okay, we've lowered the energy, and it's going to be how much by an amount hc squared over 8 pi times a volume, and the size of the volume is given by the penetration depth times the cross-section area. And so this is the situation when psi is much less than lambda, and this over here is the situation when psi is much larger than lambda. And so what you can see happening then is that the wall energy, the domain, I'm calling it wall because it's really a domain wall. The energy associated with the boundary with a normal superconducting interface is either positive or negative, depending on whether psi is greater than lambda or lambda is greater than psi. And the energy of something per unit area, that's what we mean by the surface tension. Surface tension is the energy per unit area. And so this is then telling us that the surface energy can either be positive or negative. Okay, so I think that's where I'm going to stop for this lecture. And then in the next lecture, I'm going to carry on and derive the conditions for HC2 for the onset of the superconducting transition as we vary the magnetic field for type 2 superconductors. So let's stop it here, and I'll make the next recording in a little while.